Hello, my name is Orion Junkins, and this is a presentation of research I conducted under Dr. Patrick Donnelly at the Soundbender Lab. So we sought to forecast river flow rates, and changes in flow rate affect many different stakeholders, from agricultural users to landowners by the rivers to recreational users who use the rivers or recreate alongside them. And while flow rate is directly related to weather, it's a very complex relationship that has proven very challenging to model with more traditional statistical methods. The most notable attempt has been by NOAA, and they provide forecasts for a subset of rivers in the United States, and they use precipitation, temperature, and snowpack weather data in order to forecast flows using a proprietary statistical algorithm. But their approach lacks transparency, it lacks interpretability, and it generally lacks accuracy. So they do not publish accuracy metrics transparently, but over a 110-day period, we were able to track their forecasts in order to generate our own metrics. And here you see 4 anecdotal graphs showing some performing relatively well over 96-hour forecast window, but several examples of it performing quite poorly. And we found an overall average error of 192 cubic feet per second, or about 16% for 24-hour advanced forecast. So not useless, but not very good. Many researchers have tackled this problem in more thoughtful ways and found that neural networks are very well suited to this task, much more so than traditional statistical approaches. However, these prior research solutions have faced a trade-off between accuracy and deployability. The most accurate approaches use large networks, all the available data, and really extensive compute resources, as well as long training times and slow inference to generate these accurate models. So while they were doing quite well at forecasting flows, they were very hard to deploy at scale and not practical for the real world. On the other end of the spectrum, there have been more deployable approaches that use lighter weight networks and/or a subset of available data, granting much more hardware flexibility, shorter training times, and the ability to perform rapid inference, but these approaches have been much less accurate. So our primary goal was to produce a forecasting model that achieves high accuracy without sacrificing real-world deployability. On top of that, we also sought to match or beat NOAA forecast accuracy with more transparency and greater interpretability. In order to build a model for a particular river, you need access to 2 types of data. You need river level data to quantify the flow rate of the river. And we got this data from the USGS, who provides historical and current flow rate for specific gauges across the country. In addition to that, you also need weather data, which we got from the Open Weather Map API, who provides historical, current, and forecasted data for any desired latitude and longitude. So for each USGS gauge that we desired to forecast, we selected 12 weather sites from throughout the catchment above that gauge site. From each of these weather locations, we were bringing in 11 features, over 120 time steps, resulting in a very large dimensionality. The problem with this is that high-order relationships are lost amidst the noise. It's too much complexity for models to effectively converge. And it also necessitates very extensive compute resources and training time. But to reduce the feature space in any way is going to hinder our accuracy. So to address this issue, we adopted an ensemble approach for dimensionality reduction. This mitigates the issues raised by the high dimensionality while retaining the full feature space to maximize accuracy. Our approach relies on a collection of small tributary forecasting models, each one leveraging only data from a single data site. Here you see tributary model 0, which takes in the recent level, the recent weather from site 0, and the current weather forecast for site 0. It attempts to predict the future level using only the weather data from that individual site. So you produce one of these models for data site 0, another for data site 1, for data site 2, onward up to data site n. So each of these models is only concerned with data from a single geographical location, rather than the entire catchment. So once we have all of these individual tributary models, we ensemble them together to produce an overall more accurate forecast. So again, each of these draws from a single specific X set to produce a set of intermediary predictions that only knows about a single data location, and then those are ensembled together to generate a master prediction. This approach has several key advantages. Crucially, it allows us to leverage all available data while minimizing the training time and compute resources needed. Each individual model is lightweight, and training is highly parallelizable. This approach also offers greater interpretability, as we are still able to view tributary level predictions to localize where rapid fluctuations are arising from throughout a catchment geographically. It also has a high degree of modularity. Throughout this data pipeline, both the tributary models and the ensembling model can be substituted for any variation of time series model and regression model, respectively. So in order to evaluate our approach, we conducted a simulation on historical data. So we generated 24-hour advanced forecasts for a river known as the Illinois with a USGS gauge near the town of Kirby in southern Oregon. In this simulation, our model generated a mean average percentage error of 8.57 for the ensemble model, which was 10.02% better than the best performing tributary model. This is demonstrating the efficacy of the ensemble approach, as our ensemble is outperforming any individual model that is only concerned with weather from one location. In addition, this is all done with a 12-hour train time and less than a 30-second inference time on a home desktop using an NVIDIA 3070. This is not using a supercomputer cluster or any crazy computing hardware. This is something that could be deployed into the cloud in a real-world use case. So this is demonstrating the viability of training and inference without a cluster. But that being said, parallelization across a cluster could still improve these times substantially if one was available. So to provide a more real-world evaluation, we generated forecasts for 110 days and tracked what actually transpired in the real world. In this more realistic simulation, we had a mean average percentage error of 13.62, which, while slightly worse than our simulation, was still 2.85% better than forecasts issued by NOAA during that same time frame. On the right here, you can see a graph of how our MAPE evolves as you increase the size of the forecasting window. So you can see if we're only looking 10 hours into the future, we have a MAPE of approximately 5%, while the USGS model has a MAPE of approximately 10%, and we are consistently outperforming them all the way up to a 72-hour forecast, albeit the margin narrows. So these results are promising, but there is quite a lot of work left to be done on this project. Specifically, we would like to experiment with more advanced model architectures. While effective, we are still using relatively naive models in our pipeline, and we can experiment with much more advanced time series and ensembling approaches. We would also like to evaluate the efficacy of this approach on a more diverse set of rivers, specifically on larger river systems, in order to demonstrate that this is not just specific to the Illinois and the other set of rivers we investigated, but that these results truly will scale to any type of river. We also want to experiment with extrapolating a model from one river to another using transfer learning, and the hope is that we can build a more generalized model that learns from multiple rivers, but is still able to apply that knowledge to a new river that might have less data available. It's also worth exploring the domain generalizability of this ensemble approach, as it is potentially effective for other weather-related forecasting tasks, specifically forest fire prediction and avalanche risk forecasting. Collection of our references can be viewed here. And any final questions on this project should be directed to Orion Junkins and Patrick Donnelly at the Soundbender Lab at OSU. Thank you.